So I want to discuss a particular problem. It's what we were discussing earlier. It's called the two candidate ballot problem. My handwriting is not coming out very good today. But basically, idea is there are two candidates in an election. Uh, so A gets A votes, B gets B votes. And the question is, how many ways are there to count the votes so that A always leads B in the counting. So, for example, let's say A is 4 and B is 3. So, A gets more. So, I should mention that A is bigger than B and A is bigger than B. So, what we want to do is, for example, A, B, A, B, this is fine. A, 4 A's and 3 B's. This is okay. But something like A, B, B is illegal. Okay, so what we can do is we can model this situation. This by a path. So we have a path, and again, my lines are.
Professor,
Yeah.
I didn't understand why that was illegal. So,
So A has to always lead B. So you will
okay,
have
okay,
multiple
all right,
surprises. One,
all right.
when you're starting the thing, then whoever is leading is the winner, is the eventual winner. Yeah. So we can model this by a path, and you will ask me why I have a square paper when I can't draw a straight line. That's a legal question. I have no answer to that. So, but in any case, um, if you go one step up, let me do a green path. So I have A, then B, then A, then A, then B, then A, then B. So this is a familiar situation. So we reach the point BA. And the point is that if it's always leading, and if this is a line y equal to x, then this path is above this line. So the path is always above this line. So A is your vertical step, uh, B is your horizontal step, and path stays above y equal to x. That's your model for the situation, right? So, all right so far. So this we know how many there are and so on, that situation. And um, so, but we need to make sure that this story about how to make sure that it stays above to that. So, so the number of paths uh, from BA, which do not cross, this is the required number. This is equal to number of all paths from 0, 0 to BA. And this number, or rather this number, minus the number of paths that do cross. Yeah, so this is obvious. And what we will show, let me just work out the answer first. We will show this equals. So we know all the paths from A to BA, right? So this is equivalent to this binary string, you know. So the binary string with, so there are A plus B, total length of the string, and you're choosing B of them. This is okay. So A, B form a binary string, and we subtract, and this is what we have to show. Oops. And we show that this is equal to A plus B over B minus 1. And this we can say this is A plus B factorial over A factorial, B factorial, 1 minus. So there's an extra, this is B, and there's an extra A plus A minus B, A plus B. There's an extra A plus 1 here. So A plus B factorial over A plus B minus 1 factorial. So this that gives you this extra B, and there's A plus B minus B plus 1, so A plus 1. So this is fine. And this becomes, so A plus 1 minus B. And what I'll do is I'll take A plus B plus 1 here, and then I'll do A plus B plus 1 here. So this is easy. Just check it out. I just cancel a few extra things. Fine. So the answer is um, this. And now to complete the calculation, we will use a trick. What is it called? Or something. I'll remember in a second. So we will show that there is a one-to-one correspondence between the illegal paths from 0, 0 to BA, which cross y equal to x, and paths from 1 minus 1 to B. So um, wherever I'm starting, if this point is 1 minus 1 and this point is BA, uh, there are how many horizontal steps and how many vertical steps. So horizontal steps are B minus 1 and vertical steps are A plus 1. So by the formula, number of paths here is A plus B A plus 1 plus B minus 1, which is A plus B. Choose B minus 1. So this is what I am claiming over here. Now I want to show that these are equal. So the paths cross y equal to x and so must meet y equal to x minus 1. So now let me try to make a better picture. Okay, this is y equal to x. Uh, one step below. This is y equal to x minus 1. So if I have a path which crosses, let's look at this guy. So it's crossed, then it goes up. Fine. So suppose I have a path which crosses this line and it touches here, or it goes beyond. It doesn't matter. We take the we take this last point. So it may touch here also and here also, but we take this last point, this point, and we reflect the other graph in this. So there were 3 points here. So just reflect this like this, and then here, then here, here, here. So this is known as the reflection principle, I suppose. So now you've got a path. Now you've got a path from this point, which is 1 minus 1, onto the same point. This was BA. And you take the last guy and it is reversible. The story is reversible. So this shows that the paths are in. This shows, let me put the required one. I mean, ultimately it has to reach the same point. So number of horizontal and vertical steps you have to sort of count and see how it's happening. And I think I might have made a mistake here because, yeah, this should be fine.
Oh, Professor, it might have to do
Should be
with
okay.
like uh, y equals x line not being proper 45 degrees.
Okay, any questions? So work it out. Let's see if I've got confused. I don't want to get confused live in front of you.
So are these
Professor,
called the
there is
Catalan
one
numbers or something?
Huh?
Are these called some Catalan numbers or something like that?
Yeah, yeah,
Catalan number, yeah.
absolutely. So almost there. So
Professor,
yeah,
I understood that reflecting any such path would lead me to a path from 1 minus 1 to BA, but I didn't understand how all such illegal paths would cover all paths from 1 minus 1 to BA.
well, every illegal path has to cross y equal to x. If it crosses, it must reach here. And you take the last point which it touches, and then you reflect that. So once it reaches here and it's reflected, then it starts from here and it goes wherever it goes. Right? So yeah, so any path here corresponds to one guy, and then there is a you can take any path over here, and the point where it crosses in the end, the last point where it crosses y equal to x minus 1, you reflect that, and then since this is the last point where it crosses, then everything else will be above over there. So just do a few examples and see if you get the one-to-one correspondence or not. I think it works. So anyway, this completes the proof um, that we've got that, but there is a corollary, as somebody pointed out. If A equal to B equal to M, then we get um, so here is our formula: A plus B minus 1 over 2n plus 1. So this will give you paths not crossing uh, x equal to y from 0, 0 to n. So this is 2n plus 1, choose n, and then if you work it out, this is 2n plus 1 factorial over 2n plus 1 times n factorial n plus 1 factorial. So one can write it as 2n choose n 1 over n plus 1. And these, as somebody pointed out, are called Catalan numbers. I mean, everybody in the combinatorics course needs to know what Catalan numbers is, so I had to do this theorem. So let's just calculate a few, and then I'll show you some tricks. So let's calculate Cn. Let's make a table. So 0 is okay. 1 is 1 over 2. 2 factorial over 1. So it will come to 1. 2 is 1 by 3. 4 choose 2, which is equal to 1 by 3 into 4 into 3 over 2. So that's equal to 2. So 3 is 1 by 4, 6 factorial over 3 factorial, 3 factorial, which is 6 into 5 over 3 into 2, which is 5. And then 4, I'll just write 4. So here's the trick. This I use this most often whenever I see a sequence. We see a sequence we check the encyclopedia of integer sequence. So have you heard about that?
Yes, Professor.
Yes, Professor.
Okay, so I'm not telling you. So in Stanley's book, there are 66. There are 66 combinatorial objects, all of which are counted um, by Catalan numbers. So that's a huge amount, and I'll give a few of them for your home. Okay, so we're back here. So I'll just say right now that there are a million and one combinatorial sequences um, counted by the Catalan numbers. So it's a big industry. There's the industry of Catalan numbers and Catalan Q Catalan numbers and Catalan counting and so on, which are refining these results and so on. So one of them, which I just want to say right now, is I would say brackets, well-formed brackets. So for example, uh, this path could correspond to this bracket, and AB would correspond to this bracket, two at a time. So, I mean, basically everything, a bracketing system where there's a left, the left comes, if a left comes, then you can't have two rights. So it has to be a, something that you write in a programming editor. So in a programming editor, it checks, it should not show up in red. So I don't know which color it shows up in yours. In mine, it shows up as red. So no batching trace. This is what it means. So from here, from this brackets, it's clear that what is clear that I mean even from this it's more or less clear, but from the brackets even clearer that Cn plus one is Ck and Cn minus k given from 0 to n. So why is it clear? This is some bracket of k, and this is some brackets of n minus k. So whatever the brackets are, then you bracket these two together. That's the idea. So, for example, this guy, we would be putting this bracket two at a time. No, this is fine. I mean, all this is saying is that a bracket of n plus 1 is formed by bracketing together two of these guys, one of k and one of n minus k. So if there are n minus k here and n minus k here, then you can have another one. That gives you the brackets for all. Okay, so and then k goes from 0 to n. So what I wanted to show you, so this is a recurrence relation. Again, this is a strange recurrence relation. This is a recurrence relation. And what I wanted to show you with the means of this example is how to solve it using generating functions. Okay, so now, I mean, at some point, I will do a more systematic. I think I should do a more systematic, maybe from next time itself. So there is a book which I have mentioned, which we will like to cover large pieces of functionology by Wilf. So this is a very interestingly and very nicely written book, and it contains a lot of combinatorics. Actually, it contains a huge amount of combinatorics. But so I keep it with me. I actually have a print version, um, and Wilf is. I mean, I've met Wilf. Um, I, he was an old. I think he's no longer there. So he's passed away, but he used to write very interestingly, and he's one of the leading figures of the combinatorics movement. So what happened was that the Bourbaki style mathematicians essentially they disregarded combinatorics totally, and so for a long period of time, combinatorics was like regarded as the slums of mathematics. It wasn't really mathematics. They're not there doing it, playing games or something like that, recreational math. And even though some very serious people have done some very serious, uh, papers which were very tough, it was not part of the mainstream till about, I would say, 70s and 80s when people really started solving some complicated problems. So first of all, the big problem was the four-color theorem, which nobody could prove. And then Appel and Haken proved it, but their proof nobody believed. Nobody believed it was correct. So for one thing, Apple and Haken used computer code, and nobody could verify the computer code, and they published their proof in a book. So the book was, the four-color theorem, and so they have got credit for that. But still, nobody. I mean, we call it Apple and Haken's theorem, but I've heard talks where people actually proved it now later on, and they said that they don't really. There are mistakes. Some are fixable, some are not fixable, but there are lots of mistakes. So in the 90s, graph theory became very, very strong, and it used a lot of topological methods to be able to prove uh, four-color theorem as well as some other conjectures, again using the computer. So meanwhile, there were a very famous Indian mathematician called Bose. So Bose was a Bose was at ISI Delhi, and then he went to ISI Kolkata, sorry, and then he went to North Carolina, and he had a school of people, and they became famous as solving, disproving a conjecture of Euler. They're called Euler spoilers. So Bose, Shikhande, and Parker, they came in. They were one of the first few mathematicians to come on the front page of New York Times as Euler spoilers. And then there was another student. So Shikhande is, I believe, he's still there. He's 100 plus or something. Or maybe he's passed away recently, I think. But he's a very famous guy. He was in Pune. And the next guy Bose had was Ray Chaudhary. Ray Chaudhary taught me. He came to Ohio State after that, and I was a student there. So Bose, Chaudhary, and H was somebody else. They started the BCH codes. They are very passed away. Shikhande, right? Yeah, Ayush?
Yes, Professor.
You call Shikhande? Okay. So yeah, so Shikhande passed away in April this year. So Ray Chaudhary, Bose Chaudhary, and another third guy. So Ray Chaudhary gave me a course in. So this school of mathematicians they was there, and they worked in certain areas. Then there was a school headed by G.C. Rota and Stanley. That was one set of schools. School of this thing, and then Waterloo was a place where there was a lot of graph theorists. So there is a very interesting article called "On Squaring the Circle." Uh, and one of the people over there was a graph theorist. So these guys were four students in Cambridge who were very bright, and they solved a big problem in graph theory, and it was highlighted in Martin Gardner. And these four guys basically redid a lot of. So three of them stayed in graph theory, and they more or less redid the whole thing. So there was this period when combinatorics was not taken seriously, and now it's a serious. It's like overtaken many areas, and it is all in fact all over the place. I mean, it's not just earlier it was described as the slums of topology, sometimes called slums of algebra, and so on and so forth. But now it's a very serious thing, and it's all over the place and solving very big so Rota's conjecture got solved by a guy using I don't know algebraic geometry or something big. Now he's in Princeton. I mean, so it's like very interesting stories, and you will see now. Anyway, so coming back, where were we? So generating this is not good. So Wilf was also one of the guys who was sort of instrumental in building and developing the subject. And Wilf was initially an analyst, and so we will do some of his theorems. There's a WZ theorem which we will do from Wilf, and he was also a very great writer. So this book is fantastic. So whenever I start giving a course, I have all good intentions of following a textbook, but then somewhere it goes off. So I don't know whether I'll follow it so strongly or not, but anyway, we will cover more or less whatever is there in the book, quite a large amount. And this is a good book to read in general. So one of the themes that we have to become good at is this using generating functions. So I think I will, from this time on, we want to sort of get into this theme a little bit on how to use generating functions. So as an example, we'll start with this guy. So what do we do? So what is a generating function? So given a sequence an, its generating function is now this can be viewed as a formal power series too. So what is a formal power series? I think you must have done it in your Algebra 1 course. Have you done it? Formal
Because we have
power?
done it in real analysis.
Yeah?
We have done it in real analysis.
In real analysis. Real analysis, you don't do formal power series.
Not
Oh,
formal
then,
power.
then we haven't done. Sorry.
We haven't done it.
Also, you've done power series.
Yes.
So formal power series is equal to power series minus convergence. So for example, this guy is a perfectly legal object of study. No way in hell it converges. Okay? But it's a legal object in combinatorics. So we will, well, if you haven't done, then we will do some background on that. Right now, you just say, okay, there's no convergence there, still we manipulate. So the idea is that whatever the manipulations are, they should be done in a finite way. So you should be able to calculate the nth coefficient of x to the n, essentially. But I'll go over the definitions, formal definitions at some point. Okay, so let's look at the uh, this chap right here. Cn plus 1 is equal to summation Ck Cn minus k going from 0 to n. What we do is we let c of x be equal to c of n x to the n going from 0 to 8. And this is called the ordinary generating function of Cn. So what we are doing is that this information of the sequence is it's captured in the whole series. So the series captures the entire everything, all the story of the every element of the thing. And recurrence relations correspond to. So when you have recurrence relation, what is this saying? This is saying that C0 is equal to 1, and you can calculate C2 by saying it is C um, C1 and C1 times C1. Is that right? Or 0 also, plus C0 times C2. No, C0 times C1 and C1 times C0. This is what the number is. Is that right? You're getting 2? 1 plus 1
Yeah, I
equals.
think that's right.
Yes.
So this is the recurrence relation means that from for Cn you have in terms of the previous guys, and then that corresponds to this chap. So anyway, so what we do is we multiply. Let's call this star by x to the n plus 1, and then sum over n going from 0, n above 0. So we get Cn plus 1 xn plus 1 summation n going from 0 to infinity equal to x n going from 0 to infinity, k going from 0 to n, ck cn minus k x to the n.
Professor,
Yes.
in the star, then our limit should be from k is equal to 0, right?
Yeah.
Like you've
Yeah.
written k is equal to 1.
Actually, I've written 0, but it's so squished that it
Oh,
looks like 1. I mean, I can always pretend it's my bad handwriting and not my any other mistake. But anyway, thanks a lot. So, so this is it. So this side is C of x, except it's starting from C1. So this is C of x minus the first term. And this guy, I mean, this is your classic Cauchy product or whatever it's called. This is Cx square, isn't it? So we get x Cx square minus C of x minus, this is 1, plus 1, sorry, equal to 0. So I bring these things on this side. All right, so far? Is that okay?
Yes, Professor.
And then, something I still have to, uh, then this means that C of x is, that minus b plus minus b square over minus 4 ac.
Professor,
Yes.
I didn't understand the Cauchy because one is finite and one is infinite, so I got a bit confused.
This guy?
Yeah.
Yeah, so, okay, let me do it here. So this will demonstrate to you what I mean by uh, formal power series also. So I take these two guys and I multiply them together. So what is the constant term? Constant term is when these two, so this can multiply, so all these terms can be multiplied by all these terms, right? The constant term will multiply these two guys together, right?
Right.
So I get C0 square. Now what is the coefficient of x? I can multiply this chap with this chap, so that's C0 C1, and I can multiply this chap with this chap. That's C1 C0. What is the coefficient of x square? So I multiply C0 here, so maybe I use another color. These are all done. Now I can use this color. So I want x square, so I can multiply this chap with this guy, and I can multiply this guy with this guy, and I can multiply this chap by this chap, and keep going on. So formally, I have no issues whatsoever in multiplying term by term as long as I say that every finite term I can multiply. So what is the coefficient of x to the n? Well, C0 with Cn plus C1 with Cn minus 1 and so on up till Cn with C1. And this is exactly Ck, Cn minus k, k going from 0 to n, right? So now, of course, one can do the same thing with AK and BK, k going from 0 to n. So by the way, this I can talk to you endlessly about. This is my expertise area. I have 15 ways of looking at this thing. So you can do the same thing here, right? Forget about x's now. You can do the same thing over here. So what are you doing here? What you're doing is, let's call it k going from 0 to n and m going from 0 to n and akbm. Here's another way of looking at it. So you are summing these things over all these guys, over k and over m. Yeah? So until n, you're summing over all the lattice points over here. That's right?
Right.
So you can sum this guy like this. You know? What you can do is, let's assume all these other terms are 0. Then you can sum over these lines. What are these lines? These lines are k plus m equal to n, let's say, akbm, and then you are summing over n. Summing over, well, now this will confuse you. So k plus n is, yeah, this is fine. So let me remove this guy. It's unnecessarily complicating. Let's assume everything is summing over the whole thing, entire plane. So what is this chap? This is these lines. And then you can think of it as replace m by n minus k, and you can say it's k going from 0 to n, ak b n minus k. So this is essentially what Cauchy was doing, and this is called the Cauchy product. This is called the Cauchy product. And in analysis, I don't know if you did that, but there's a long and painful proof of why it works. I mean, there has to be some kind of convergence and so on. Okay, but this is the basic idea. I'm sure Cauchy was proving this idea, right? You can put A0, A1, whatever over here, and then you get the same. Okay,
Professor,
does that make sense?
yes, yes, Professor.
Yeah.
Professor, so is the continuous analog of it is the convolution?
Yeah, this is called convolution. Yeah. So yeah, exactly. You're right. So sometimes you integrate also, and you say y minus x, something like that, right? I mean, this is the
Sorry.
same thing. You're multiplying. So integrals are equal to sums. In general, integrals are equal to sum, right? I mean, this s, if you extend it, then it looks like this. Magnify. So they're essentially the same thing. Am I confusing you? I think I'm confusing you. For a change, I'm not confused myself, but I'm confusing you. So that's a good positive thing for me. Okay, is that okay? Shall I go on?
Yes, Professor.
Professor, just one thing. So you are saying that there is a real analytic proof of this. So proof of the fact that two converging sequences can be multiplied in this way?
Yeah, something like that.
Okay.
I mean, a double sum basically converges if the individual guys converge and so on.
Okay. Thank you.
So, yeah. So, I mean, yeah. So, formally, this is how we argue. I mean, here I don't really care. I just care that the kth coefficient is okay. So, let me do, before going back, because this is topical. So I'll cover this more detail again. So this is aside one, aside two. Um, you know how you make polynomials. So a0 plus a1x plus a2x squared and so on. So this f is a field, ring or something. So this I can just make a infinite thing. I can define plus, product, right? All those things on this. And then depending on f, one can define whether it's a field. We can figure out whether this is the ring of formal power series. And depending on the properties of this f, one can figure out whether it is invertible elements, which are not invertible. So does it become a field? Is that you can talk about whether it's a Euclidean domain, it's a UFD, things like that. You can work on all these algebraic objects. All this is just an infinite string. I mean, x's are nothing. So in I don't know what book you use for algebra, but you can think of x as this infinite vector and x square as this infinite vector, and then you don't even have to have x's there. So these are indeterminates, and you do the addition, subtraction, and you can see that you can define multiplication. So this can be a definition of multiplication. You can define multiplication like this, and it's pretty obvious. It's like defining extension of multiplication in fx. So these are square brackets and these are round brackets. That's the only difference between them. Okay, and the degree issue doesn't work out. So you don't have a UFD and all that in this kind of scenario. But anyway, degree is not there. So this doesn't work in ring of formal power series. Euclidean domain, I don't know. So anyway, you can define various things. Okay, let's get back. We were here at the crux of a discovery. So we had Cx is 1 plus or minus 1 minus 4x. So 2x. So now question is which one? So it's is Cx equal to 1 plus 1 minus 1 plus 4x over 2x, or is it equal to 1 minus 4x?
So that's 1 minus x up 1 plus 1 minus x.
Sorry, is that what you're saying?
Yes, Professor.
Okay.
Oh, Professor, you'll get complex numbers for this, right? If x is positive.
Well, x is not a number. I mean, we just talked about x being an indeterminate. So x is just a symbol. So yeah, I mean, okay. So let me address that a little later. Let's just see. So what happens when x is 0? So I usually be teaching this to all my calculus students, right? If x is 0, this is of the form 1 plus 1, that's 2 over 2 times 0. So limit does not exist. But you can take the limit here. So you can take the limit here and you get the answer 1. So this is the one we choose. So this is the right one, and this we reject because C0 cannot be defined here. So this is the guy. What this is saying is that C of x equal to 1 minus 1. So we have an expression, 2x is an expression for the generating function of Catalan numbers. Okay, so yeah, so now what does this mean? What is square root of 1 minus 4x mean? So, of course, you know the answer. Somebody just mentioned you can do Taylor series expansion. Yeah, so do you know the Taylor series expansion of this? Um, I could, let's see, we have half an hour. Let me, I want to spend some time. So we are on till 6 p.m., right? So I want to spend about 15-20 minutes on Sage. Um, but let me just give you some ideas here. I mean, this is of course probably a repeat, but this is so. So let's see how did Newton discover the binomial theorem? So what is it? We already know this guy. I mean, I really don't know the answer, but this is one potential answer. Certainly, it wasn't an apple hitting him on top of the head. I mean, he was playing around. Okay, so we know this for n equal to 0, 1, 2, and what's the difference here? This difference is this is 1 minus 4x raised to 1 half. So the difference is this guy right here. Right? So if I want to replace n by, suppose I want to replace n by something, by a, what do I do? So this side is no problem. I know how to define 1 plus x raised per a. And that's no big deal. But this side is a problem because this n choose k business can only be defined as, and this is going up till n going to n. So first thing you notice is that this guy can be written as k going from 0 to infinity of n factorial over k factorial. So hang on, I don't want to write it like that. I want to write it like this is n into n minus 1 into n minus 2 and so on until n minus k plus 1 x raised to k. So why can I write n going to infinity?
Because at n the products would be 0, n minus n would be 0.
Right. So if I look at this term right here, n minus 1, n minus 2. So if k becomes equal to n plus 1, this term becomes 0. So may as well make it this. So I've got rid of one of the problems, one of the things where I could have a problem potentially, but I have an infinite series. Okay. Now this one I write like this. I write minus 1 raised per k over k factorial, and this one just for the sake of this thing I'll write minus n plus 1, so on up to minus n plus k minus 1. And this is in our notation. Oh, there is an x to the k also. Minus x raised per k over k factorial, and then minus n sub k. Now one can replace everything. So what do we get? We get, in fact, I'll replace x by minus x2. So I'll get 1 minus x raised per a is equal to summation, and this is a sub k or k factorial x to the k. And since it's an infinite series, I need to calculate when it converges. So I do this. This is required for conversion. So I've guessed it. From a finite sum, which is known from centuries, to, and this is why it's called Newton's binomial theorem. It's not called Chu's binomial theorem or Pingala's binomial theorem or anything. It's called Newton's binomial. So, um, so this is a guess, and actually Newton calculated from here. He actually multiplied. He tried to do all this, whatever he's getting here, and he checked whether you're getting 1 plus x here. So you can see calculations of Newton where he writes it out with this notation over here, and then he gets then he checks whether he's getting formally 1 plus x. So you can try that if you wish. You can see that Newton sort of guessed somehow formally, and then he tried to prove it, and of course one can prove it using calculus. So let me give you an outline, because this is not a analysis course, so I won't do this.
Oh, Professor,
Yes.
just a small question. So, a bit above when we replaced negative n by a, so on
Yeah.
the left hand side, shouldn't we get 1 minus x to the power negative a?
Yes. We do.
Oh, on the bottom, in the final concluding line. Yeah.
Yeah. That's right. I mean, I want to write a here. That's why I've written a minus a there. Not a. So a is by the way, a could be any complex number or indeterminate. So let's see, what is let f a of x be this guy, the sum, and show that f prime a of x is equal to a f a plus 1 of x. This is some proof. So this requires uh, absolute convergence in this domain, some epsilon. So you want to interchange the derivative and the sum. So you can show this. Then you can show that f a of x minus f of a plus 1 of x is equal to z f a plus 1x z by z a. So I have z somewhere there. And then from the first two, you show that f prime a of x is equal to a over 1 minus x f a of x, and we already have f a of 0 equal to 1. Now you solve this differential equation in part C to get f a of x is equal to 1 minus x raised to minus. Okay, so I mean, you can fill in the steps if you want. I'm going to omit it. Yeah. I mean, I think for a combinatorics course, it's not really required. So if you were doing classical analysis, I would do this, but I may give a better proof later, or may not actually. Let's, yeah. So I'm not. This is not a combinatorial proof, so I'm not too interested in doing this. So any questions before I do a small demo of Sage? Any questions?
The assignment, can we submit the notebook files?
I think if you do screen grab and all, that would be better. I mean, just copy paste some, just show me the output. Here it is. So this is Sage. I just downloaded Sage. So have you guys got Sage now? Have you downloaded it? I mean, the first thing you do is do 2 plus 3, and then you can do a lot of items. And I have a where is it? I have uploaded an assignment which has disappeared. Here it is. So there's a bunch of commands that you can try to make sure that you know how the basic thing is. The last one is an interesting one, which I wanted to show you. So one can do polynomial ring with rational coefficients, and then you can use this q as a um, as a variable. And what is interesting is, suppose this is then I can use a command called coefficients to get me all the coefficients. And this gives me the Pascal's triangle. So this is nice. Then I've written a program for say Fibonacci function. So this is a if you put a cached function, I don't know if you have you done dynamic programming? Cached function does it it keeps track. It does the dynamic part for you. Okay, so just put that whenever you are doing a recurrence relation. I mean, sometimes you can tell the difference. So Fibonacci 1k, if k is equal to 0, then return 0, else else if k is equal to 1, return 1, else return k minus 1 and k plus k minus 2. So this is a cache function, and then I can print all the. So the only difference between Python 3 and Python 2, as far as I can figure out, is that you put a print command in brackets. Otherwise, all my other programs work. So I had Python, I mean, I had the previous version of Sage, so I just downloaded this week just to see whether it works or not. And there is a simple way of solving problems on Sage. And what you do is you type how to represent sets in Sage math. So don't do just Sage, do type Sage math. And then there you go. Whatever you get, you just look at it and it says, it gives you the method. So William Stein is the guy who started Sage. He was irritated with something and then he did it. He's a number theorist. So Sage has a lot of stuff for number theory, and now many people have taken on over uh, developing this. So just you see the examples, and by and large you use the don't use. Um, so I was using, for example, the I keep forgetting the way to get this thing. Um, so almost all the theorems um, that you have studied so far and are expected to know, including Bhatia's assignments, many of them, the Sage is very useful to do them in a very short time. So I haven't done them, but I mean I can bet you that it's easy, easier if you use Sage to do those assignments. It's a trick. Don't tell them I told you. Okay. So essentially, it's a painful process to load it and to get it started. Files. So here is a subsets listing. So this is a homework problem. I just implement IN as a set, and I can list all the subsets. That's your homework problem altogether. And you can use the cardinality function to list the cardinality, and we get the same answer. You can. This is exactly what we did for the binomial theorem. You can even call OEIS. Sometimes it works. Might have gone out. No, it's gone out. So in 9, OEIS doesn't work somehow. Earlier I used to call OEIS over here. And yeah, this is nice. What am I doing here? This is a coin tossing experiment. See if it works. So I count the number of heads in 100 tosses of a coin. Okay, this is taking a long time. So if you see over here, I'm tossing coins, so random integer 0 and 1, and I take the sum of it. So that means if it's 1, then it's a head, so I take a sum of heads. And then I repeat the experiment for 1500 times, and here you go, I get some kind of a normal distribution. So Sage is extremely useful for many things. Here it is. So you can make a matrix and you can take its inverse. And you can multiply the matrix with the inverse. This is what I did earlier. This is my rising factorial. And I can take coefficients. I can do all kinds of stuff. Okay, so yeah, I'm done with this. So this list is a key thing. So 2k minus 1 for k in 1 to 10. This is a list data structure. And almost everything, this is a very nice data structure. And you can do list plot, you can do all kinds of, you can put all kinds of things. So actually Sage is, you see k in 1 to 10, it's got mathematical notation. That's why I like it.